Yeah, hi, welcome to the part 2b. So we still stay within one-dimensional convolutions as we were doing the previous video, but now we will move from doing this more intuitive part to more of a formalization, and then we will look at other features or other things which are important for convolutions. So let us look first at this formal definition. So to better understand how convolutional kernels are learned, we need a bit more formal definitions. And the first thing which we'll do, so we are still in this one-dimensional input sequence, right? So we have basically the sequence X, which is our input here, and we're going to say that that one is now going to be n-dimensional, right? So these are n floating point numbers and real numbers, and the second thing which we will be having is a filter, right? So we have a filter, and that filter will also have a certain length. Now, this length is a bit written down in a bit of a weird way. So it says here that it's 2m plus 1. And what that basically means is that because m is just a normal natural number, the length of this filter will be uneven. So we will only, in our formalization, only support uneven length filters, meaning a filter of length 1, length 3, length 5, 7, and so on. Now, what does this convolution exactly mean? So what we have in this formula here is basically trying to write down what the meaning is or how you would compute one of these outputs of the network. All right, so this is the output h. And if we look at a certain position of h, so the position t in this case, we see that it is going to be a sum of things. Now, we have seen before what sum that was. So it was basically the sum of these input neurons. And the way we can write it formally down is to say that we have to look into the vector x and multiply that with weights from k. Now, which part of x do we have to take? Well, we will basically be looking, so this is position t, let's say. We look at position t in vector x, and we go m steps upwards and m steps downwards, right? So we basically go from minus m to m, and that is being subtracted from t. So it means we are in x, and we go basically from that position m steps up and m steps down, and then we multiply the value which is there with the corresponding value in k. We sum all of this together, and that is basically going to be the output of this summation. After this step, you still have the bias, we still have our nonlinearity, but this is the essence of the convolution. It's really just this multiplication, or this dot product actually. Now, as we mentioned, so this filter k, right? So I'm talking about this box here, for example, our silence detector or whatever thing is being trained there, or whatever thing this filter actually means, is learnable, right? So we want to learn that filter k. And now, basically what that means is that we're going to use samples, right? We're going to use data samples and backpropagation for learning this filter. And that means that we have to update the filter weights based on a certain loss, right? So, and that loss is this loss which is shown here, and that could be, for example, it's depending on the convolutional response at all the places, and that's corresponding, for example, to the cross correlation for the classification. So, the better your classification, the lower your loss will be. And then what we basically need to do is, for computing our updates to the filter, right? So we want to learn the filter, so we want to update the filter at every iteration. We need a gradient. So we need to know in which direction we have to change the values in our filter. And so basically what we have to do is we have to compute the derivative of the loss. And now we basically get an expression in which first to the point of this last term. So this last term is going to be always 0, except when tau 0, so tau 0 is basically referring to the index of the weight in the filter, which we're updating, is equal to tau. So it's equal to this exact position. So basically they really are next to each other when the filter is applied. The next thing which you observe when you have worked this out is that the update of this weight is taking in consideration all elements in the input sequence, right? So we are ranging from 0 till n. So we take all elements in the input sequence, and we see basically how they are affecting the update of the position of the filter. And so what that means is that these weights are really shared across the entire input. And the MLP is learning an independent weight at every position. So the advantages of working like this, so basically applying this filter over the whole data set, is that convolutional neural networks are much smaller than MLPs, right? So when we have one of these feature detectors for noise, as we just showed, it has only 3 weights. That's it. If you would want to have somehow a silence detector for a complete, like you would just design it with an MLP and not with a convolution, you would just need a huge network to be able to detect silences, right? So we have an extremely well-working parameter efficiency. The next thing is that convolutions can learn or become basically very powerful pattern recognizers, right? So for example, for the silence thing here, just based on silences appearing anywhere in the input. Yeah, so if you would use an MLP, basically you must learn an independent silence recognizer for every possible position. So we also have a very good data efficiency, right? So we really use our data to the fullest extent. Then convolutions can also recognize silence patterns regardless of where it appears, right? So we can just have that silence anywhere because we're just going over all the data. Even if we have never seen a silence, let's say, at position at 10 seconds, our convolution will be fine because it's really trying to see whether the silence occurs just anywhere. So to summarize, the convolutional neural network has very large generalization improvements, right? And important to mention here is that so the number 2 and 3, by which I mean these 2 bullet points here, they are just a consequence of the convolution being translation equivariant, right? So we'll come back to this equivariance later on as well. Okay, so what have we done up till now? Well, basically we have been looking at filters, right? And we have seen that, okay, we can create those filters. We discussed that they're basically just an MLP in disguise, right? So it's an MLP, but can move around in the data, meaning that we can convolve them over the input, which creates then our output vector. Now, we still have several problems, right? So it's nice to have this silence filter thing, but we are not just interested in silence. If we want to answer the hard questions which we were talking about, we will need something more, right? So we need to, well, for example, detect silence is nice, but we might also have to detect certain regions with a lot of noise, detect certain rhythms, detect certain. So we need a lot more filters, and we need multiple of them, right? So it's not just one filter; is clearly not enough. The second question which we need to answer is, what do we do at the start and the end of the data? Right? So we have always been looking at sort of the middle of the data, and there things work nice, but we have to also look at start and the end. Then you have already seen that an MLP typically consists of more layers. So right now we are just looking sort of at one layer and we see what happens, but we also have to think about what happens at the next layer. And then the final thing there is, how do we get the dimension down? Right? So what we have been seeing is basically that we go from a certain dimension, we apply our filter, and then we are still left with the same dimension in the output. And what we need in our network basically is we need to go to a dimension which is equal to the number of classes, for example. And so we need to get that dimension much smaller as it is. So let's start with the need for multiple filters. So as mentioned, so we need to have a lot of filters for feature extraction, right? And the point is that our design as we have it does not limit us to just have one filter. We just had one because we just only made one. But in theory or in practice even, we can make as many filters as we want. You want 2 filters, you make 2 filters. You want 10 filters, you make 10 filters. The only thing which will change is that instead of having just one vector as an output, is that you will get multiple vectors as an output. So the output does not just stay one vector, but instead it will be one vector for each of these filters. So this filter creates this vector, this filter creates a second vector, and if you have more, then you will create more of these vectors. So that means that basically you start from a certain dimension, right? So it is a 1 by n or n by 1 vector, and you move to a dimension which is depending on the number of filters you have. Now, this output, which we'll actually call the output volume, because it becomes really a volume. Now it's a 2D matrix, but later on it will become more. So now we have something which we call the output volume. Okay, so we have been looking at these multiple filters, so we are basically fine. So if we need multiple filters, we can make multiple filters. Now, one thing which we saw is that we went from just one-dimensional output to more dimensions, right? So, or rather, we went basically from a vector to a matrix. So the question is, what do we do on the next layer? So obviously we cannot do exactly the same. So what we will be doing instead is we basically define our convolutional operators different on the next layer. So when we apply convolutional operator here, so we now get the data which we just got from our multiple filters, two in this case. And what we now see is that when we want to create a filter here, also that filter itself, so this is just one filter, so this is just a normal filter as we had before, one filter, but the thing is that it gets a second dimension as well, right? So this filter now applies over the complete data. So it means that this position gets multiplied with this. That basically get a dot product in which you get 8 components, right? So this with this, this with this, this with this, and so on. And so also this filter, we can just convolve over the data as we did before. So as you can see, so basically we apply this filter on each of these components, and then we get an output. So that means that we are able to go back to an output volume which has just one dimension in this case. Again, you can also have multiple of these filters, and then we would, for example, stay with 2 of these output vectors as well. And one important observation here is that if you think about the meaning of the filter, so in the first layer we were talking about the fact that basically like the silence filter, if you look at it, you can see that that filter itself is basically a silence, right? Now the point is that these filters on further layers, the meaning of the filter itself is just really depending on the meaning of the filters on the previous layer, right? But they become more complex. So if you have a filter like this one, after you have applied the filters on the previous layer, the meaning of this filter is a sort of combination of the previous filter. So if you have a silence filter and you have, before you had, let's say, a high noise or let's say a very high frequency noise filter, then this filter which is here is basically going to be a combination of these two. So it might mean, for example, you first have a silence and then right after it you have a high-pitched sound. Then if you go much further into the network, let's say more after several layers, these filters or these neurons which are then producing the output, they're going to get more and more real semantic meaning. For example, they might become things like, okay, this is not just a high-pitched noise, but it means that there is a certain beat in this music. And further, you get again more enhanced feature. At some point, you might be able to classify the music with the output. Okay, so we have talked about multiple filters and what we can do in the next layers of this convolutional neural network. Now, there is still one issue at the start and the end of the data. So let's look at an example. So now we are completely at the start of our data, and the problem is that near the boundaries we cannot really apply our convolution as we normally do. So what you see here is still okay, right? We can still apply this, but we get a problem once we go one more up, and the problem is, of course, that we don't have anything as an input for this first value in our filter. So the solution, well, the first solution could be to just ignore the boundaries, right? So we basically just start one position lower. And as you can notice, that also means that we will basically reduce the dimension. So we will cut off a bit from our dimension. So we will start a bit later, and at the bottom we will have the same, so we will also be cutting off one value. So what that means is, of course, that information at the boundaries gets lost. It's just gone. The other solution, which is the most common solution, is to basically pad the boundaries. So padding basically means that you're adding extra values which were not in your original data, and then still apply the filter. So we add this zero padding here on the top. Then we can apply our convolutional filter and then still create an output for it, as shown here. So we are just adding this extra value, shifting the filter up as we usually do, and we still create an output. Typically, the padding is done with zeros. That does give some sort of artifacts because you don't really know what the value should be. But still, it typically gives better results as not padding and reducing your data size. Okay, so we have now seen what we do at the start and at the end of the data. Finally, we have to talk about how we get the dimension down. Not in the same way as we had in the start and the end of the data, because there we were really just like cutting off data basically. But here we want to sort of in a controlled way get the dimension lower. Now, there are basically two solutions. The first solution is what is called taking larger steps of a filter or increasing what is called the stride. So that means that when we were applying our convolution operator before, what we basically did is we were applying it on these three things here, right? And then we made a step, and then we were applying on these three things, and we made a step, and then these three things. Now, nothing is stopping us from taking bigger steps. And that is what is shown here. So this is a stride of 2, right? Stride of 2 means that you're basically going to make steps of 2 values at a time. And now, what this basically does is it's going to reduce your dimension with a factor which is equal to that stride, right? So if you take 2 steps at a time, you're basically going to have a reduction with a factor 2. If you take 10 steps at a time, then you're going to have a reduction with a factor 10. This also means that to make this actually work, your input dimension must be a multiple of that stride, right? So if you want to, if you make 1 step at a time, it doesn't matter what your input dimension is. If you take 2 steps at a time, you must make sure that sort of in the end your things fit, right? So that your convolution operator properly fits within, within what you're convolving over. Okay, so that's one way to get the dimension down. There is also a second way. The second way is what is called a pooling layer. Now, what pooling is going to do is that it goes over the data, very similar to convolution actually. But instead of a normal convolution, it's going to apply a deterministic function, like for example the max function or the average function on the input. And in this case, the stride is typically going to be equal to what is called the pool size, which is the length of the pool. I will show you now. So let's imagine that we have a pool size equal to 3, meaning that the length of our pooling operation is 3. And what it's going to do is basically try to find the highest value, which in this case 0.3, and that's going to be also the output of our operation. In the next step, it's also going to find as the maximum value, minus 0.9 in this case, and going to put this as the output value, and the same is happening here. So the big difference with what is happening in the previous example with the stride, I mean, it's a bit similar, right? So there's also jumps happening. The big difference here is that the function is really deterministic, right? So it's a max. It just takes the maximum value of what is in the data. Okay, so okay, I already mentioned this, but so instead of doing a maximum here, what we could also do is take an average. So we would just compute the average of these 3 numbers, and that would be the output of the operation. Now, obviously, what you can see here is that this also reduces your data by the length or the pool size. So just as we did in the previous examples. Okay, so that was it for the 1D convolutions, right? So what we now have is basically something which can be used on one-dimensional signals, like for example sound. And what we will do next is basically take that knowledge and move it over to what we do when we have 2 dimensions, 3 dimensions, and in general n-dimensional data, and apply the same, or want to apply the same techniques.